good lunch. We do not have a siesta, but we will enjoy the session here. This morning there was one talk that was not there, so that's going to be given by June. First of all, from University Exeter. So that is added to this one. So you please, everybody will talk about 12 minutes, and so that we have 3 minutes to for the this talk. Okay, please.
All right, is this one on? Can you hear me? All right. So, hey everyone, it's great to be here, and it's great to see an initiative like this. And I'm very pleased to be able to be here in person, finally. So I've been working with UAVs, or drones as they are called, for a few years now. And while I would argue that anyone can fly a drone given minimal training, collecting high quality scientific data is a different matter. In this short talk, I will briefly introduce some key concepts, challenges, and workarounds with a focus on using thermal cameras and drones. Oh, yeah, that's great. I need it. Right. Yes. So first I will introduce an image-based modeling approach that most of my work is centered around. It's called structure for motion, SFM for short, multi-view stereo, MVS for short. And I think many people here use this approach, but it's important for my talk that everyone has at least a basic understanding of the key principles of this method. And then I will go on to talking about coupling drones with thermal cameras with a focus on theory due to the short nature of this talk. But I will be keen to talk more in detail after the talk if anyone's interested. So this image-based modeling approach called structure for motion multi-view stereo. What is this? What is this approach? So it's an approach which utilizes different kinds of software, both proprietary and open source, and allows the user to create a 3D model from a sequence of overlapping 2D images. So one of the key things for this approach is that you have to have overlapping images that you find matches between them. And the two major outputs from this approach is that you get an orthophoto or a geometrically corrected image mosaic in which you can measure distances or the size of objects. And you also, as I said, you get a 3D model. So most people use this approach. They use this approach with regular digital cameras. A digital camera, it operates in the red, green, and blue wavelength spectrum, while a thermal camera, which is what I'm trying to use, operates in the long-wave infrared spectrum. And the thermal camera records the thermal radiation emitted by objects. And you can use this thermal radiation to estimate the temperature of objects within the scene or to quantify the material properties of the objects. Additionally, you can use the thermal radiation to map the wetness patterns in the field. For example, as natural drainage channels or a leaking water pipe. So when I say material properties, what I'm referring to is mainly emissivity. Most people here, again, are probably aware of what emissivity is, but I will anyway briefly introduce this term. So emissivity is a measure of how well an object emits thermal energy, long-wave infrared energy. So in practice, this means that two objects with exactly the same temperature, they can look very differently on a thermal camera, just because they have different emissivities. And we can see one example of this in this image here. So the hand, we can see a hand here, and we can see that it has a ring on its finger. And these two objects, they should have a very similar temperature, but just because of emissivity, the metal ring looks much cooler than the hand. There are a range of different thermal cameras that you can use, and many of which are small and cheap enough to attach to a drone. I'm personally using something called a FLIR Duo. It costs around 1,000 euros, and it has two sensors. It has one regular red, green, and blue sensor, and it has a thermal infrared sensor. So you can store these two images separately or combine them into a blended image if you want. And you can see two examples here of blended images. And we can clearly see that when trying to blend the images together, it's not always perfect. So we can see that there is a discrepancy here between the thermal image and the visible RGB image. And because of this, because you really don't want to add more challenges than you need, I would recommend that you just process the images separately. In terms of flight planning, using a thermal camera is very similar to using a regular RGB digital camera, just with one exception, that thermal cameras, they are more prone to motion blur than digital cameras, so you have to make sure that the camera is stable and that you're not flying too fast. So, for example, if you're using a low-cost thermal camera, as I do, using a fixed wing is out of the question. And obviously, as the thermal camera only stores temperature, you should process the images as a single band image. And another problem is, so one of the key challenges when working with thermal cameras, for me personally, is that, as I said earlier, one of the key principles for this image-based modeling approach is finding matches between overlapping images. And thermal cameras, so thermal images, they have a tendency to produce repeated patterns. So the thermal signature of one area in the field can be very similar to the thermal signature of another area in the field. And because of this, the software tries to match these two areas together, while in reality, they shouldn't be matched together. And this creates distortions in the final model. And another challenge is that there is most, if not all, of the thermal cameras, they use something called an uncooled sensor. So there is not a device on the camera that actively cools the sensor. So over time, there will be a temperature drift. And we can see some examples of this here. So there are two images of the same area, very close to the same area, and I created some circles just highlighting some of the key differences between these two areas, just because of what I think is a temperature drift, but it could also potentially be viewing angle differences, for example. So, as I hinted at just now, is that camera stability is crucial for using thermal cameras. So an object can look widely different just depending on the viewing angle, just from what angle you're looking at this object, which obviously makes this approach more difficult to use. So some of the things that I'm trying to use to overcome these challenges. So the first approach I'm using is to use a low-cost calibration target. So basically, I'm using something with a known emissivity, which is electric tape in my case, and I'm wrapping it in just a metal sheet, and then I'm using this. Then I'm taking a picture of this electric tape just before the flight as a reference point, and because I have this reference point just next to the field that I'm serving, I can estimate the emissivity in the field. And also, as I'm taking a picture of the same calibration target when I'm landing, I can get an idea of how extensive the temperature drift over time has been while I'm serving the field. And if need be, I can compensate for that. Additionally, I'm using aluminium foil reference targets. So one thing you might notice when you're looking at these thermal images is that they're quite abstract. It might be difficult to orient yourself in these images. So to be able to better orient myself in these images, I'm using aluminium foil targets with a very low emissivity. And because of this low emissivity, I can easily locate them in the field. And if I distribute them in a known pattern, I can just easily look at the thermal images and know exactly where I am in the field. And that's about it. Thank you.
So are there some questions for you? All the way back? Do you have a question or? No, it's just Well, maybe I have a question about the temperature in terms of the calibration.
Mhm.
So when you do it before the flight, you do it at the same altitude, or how is that, or you measure it before you launch the drone, or?
Yes, I do it just before I launch the drone. Yeah, so I'm mainly interested in, so what's important when trying to measure wetness patterns, which I'm doing, is the relative temperature differences. So it's enough for me to just, measure it from the ground when I'm launching.
What is the maximum flight height you would launch it?
So I'm flying at 60 meters now, but obviously it depends on what kind of resolution you want to do. So I'm getting around maybe 20 to 30 centimeter pixel size resolution.
Okay. Because what we did a couple of years ago in barracks is that if you fly over the irrigated field, the water vapor content is very much above a wetter surface. You need to compensate for that. If not,
exactly.
so that's something that sometimes a little bit more difficult. Another issue is related more in terms of the emissivity part. Quite often, if you have a mixed pixel, like 50% vegetation, 50% bare soil, that can be another issue.
Definitely. That's one of the things I'm trying to work at now, trying to compensate for the biomass. There's been some studies that are looking at this as well.
Yeah, I think for this group, that would be very interesting that some of these kind of related to science issues, we can actually attack it, because from this morning's presentation, several of those things were looking at more maps for vegetation. Once you move to a thermal part and a microwave part, it becomes more critical to look at exactly radiometry, emissivity related.
Sorry,
Yes,
just a quick
Flora.
question. Can you please repeat like how the target is made and exactly what is it?
I think I should have a picture somewhere, but it's just a metal sheet that so you know what electric tape is? It's just this thin layer, and it's a high quality electric tape that I just put on top of this metal sheet. So the metal sheet is highly conductive, so it should be the same temperature as the ground. And because I know the emissivity of this electric tape, so it's just basically a square of metal that I put electric tape on.
Okay.
Any more questions?
Yeah, all the way there. Yeah.
I'm using Midnight at the moment. I can't say that there are no issues. Well, so the problem at the moment is in some areas it's looking alright, and in some areas there are false matches still between areas that shouldn't be matched together, which are creating distortions in the final model. So I'm still working on trying to compensate for these distortions.
Okay, thank you. Maybe perhaps another question is, did you ever use black body to do the calibration?
So we are planning to do that. So there is a black body calibration unit just close to where I'm based.
Okay.
But as I'm only interested in the relative temperature difference, I would argue that it's not worth the cost to do that. It would make it interesting more, like it would make it easier to publish papers probably. So it might be worthwhile to do.
Okay. Thank you very much.
Thank you.
Okay. Yeah, he has another question.
That for calibration, what we do is taking, in order to have the span of the dynamic range of the sensor, we take water, cold water with ice, and boiled water, or water that is actually with the temperature of the field, and then we have the span of the dynamic range of the sensor.
How do you measure the temperature of the water?
Just put the thermometer.
Right. Okay.
We don't need any thermometer, regular one. It's a very accurate temperature.
You need to have some water point in the area. Indeed, when you fly it, usually people use that also as a target reference.
Water.
Okay, thank you very much. Yeah. How do we? Can you just operate it? Okay, no. Okay, our next speaker is Brigitta Toth from the Hungarian Academy of Science. She will be talking about obtaining soil hydraulic parameters to enhance soil moisture prediction with UAS. Please.
I'm Brigitte Toth from Hungary. I'm a soil scientist. My focus is on how to predict soil hydraulic properties and how to map them. So maybe you are curious about how it is connected to this cost action. So for a specific task, when you monitor the soil moisture content with the drones, and you needed to calculate it for the root zone, one thing what you might need is the soil hydraulic properties, so the capacity. Of course, other things you are needed, the models. For example, Salvatore did research on this topic, how to calculate the root moisture content, and for it, hydraulic pedotransfer functions can be, let's say, something what you need. And also, if you have spatial information on it, then it's already much better. So I would like to show you an example how we prepared the soil hydraulic maps for Europe at 250 meters. To derive the pedotransfer functions, we needed a soil hydraulic data set in which we had measured the data on soil properties which are easily available, and of course the water content connected to the head, the metric head, and hydraulic conductivity connected to the water content or hydraulic head. So to derive the European pedotransfer functions, we used the European Hydrological Data Inventory. This was created by the collaboration of European soil physicians. For example, Nunzio took part as well. So it was a very nice collaboration, because really those people gave their data who are expert on the field. So it is high quality data. And what made a step forward, because maybe you know HyPress because it is well known, it was before EU HYDE, it was the data set which was available for Europe with the soil hydraulic data, with a quite good representativity for European soil. So why it was needed? Because there were areas in the Mediterranean, it was not very well covered, and in the HyPress, the sandy soils were more represented. And what was a step further in this EU HYDE, that now we asked if chemical soil properties can be included as well, and there are some information on land use as well, which is again a plus. But at the end, for example, the land use could not be studied, how much effect it has on the soil hydraulic properties, because most of them were from croplands, so there was nothing to compare. And just a quick view about the data set. So the data set contains more or less 18,000 samples, which is more or less to 6,000 soil profiles. And here you can see what is the characteristic soil texture classes based on the organic carbon content. Of course, it was we do not have every chemical and physical data for all the samples, but it was a great step forward that it was possible to analyze the effect of the chemical properties on the soil hydraulic properties. Then let's see a little bit how the soil water content looks like by texture classes. It is not really visible, but it is for the subsoils. and by the USDA texture classes. So what you can see that based on the metric potential, what is the water content. And basically, these were what you can see, the fitted lines were the class pedotransfer functions when we worked out the predictions. So to make it clearer, why I say class pedotransfer functions, because we worked out the predictions for different input parameters to give the possibility for the users that if they have information just on the FAO texture classes, which is the modified texture classes, it means that 5 classes are differentiated, and you know only that your soil is the topsoil, which is considered 0-30 centimeter, or you have subsoil under 30 centimeters, then there is an option how you can calculate these parameters. And as I mentioned before, we could analyze the effect of certain chemical parameters. For example, what was new, that the calcium carbonate and the cation exchange capacity and also the pH could be studied at European level. And what was the result? Here you can see that for the studied soil hydraulic properties, so these are the most used one. This is the saturated water content, the water content at field capacity, water content and at wilting point, the saturated hydraulic conductivity. This is the moisture retention curve, so the Fangenukten parameters. And then the Muellen Fangenukten parameters to describe both the moisture retention curve and the hydraulic conductivity curve. And what you can see from here that, for example, for the saturated water content, the pH was found important, which is new because before for soils from Europe, it was not found important. It was like that Tomassel and Hodnet was analyzing the soils from South America, and he found that it is important. And then it came out that yes, pH is also important in this case. Okay, maybe if we would have information on structure, if we could have used it, maybe pH would not be here, but then it helps. And for the field capacity and the wilting point, if you have sand-sealed clay content and organic matter, then it is you can predict well the soil properties according to the present results, and the chemical properties did not improve further the predictions. And also what was new, that also for the moisture retention curve, the pH significantly improved the predictions. For the hydraulic conductivity, you can see that more detailed information didn't improve the predictions. So it can be interesting why it is that. Maybe the main reason is that the measurements on the conductivity were done with different methods. So it can have a great effect what kind of value you get. So then the effect of bulk density or organic carbon content, which we would think that it has an important effect on hydraulic conductivity, didn't come out. And then when these pedotransfer functions were included in an R package. So if someone would like to use these predictions, it is built in there and is easy to use. You just have to be aware to name the input parameters in the same way like it is in the PTF, but it is explained in a file. And one more thing which is important to mention here, that here you can see that LR means that linear regression was used to derive the predictions in most of the time. We tested also regression trees, and the MS means the class pedotransfer function. So it seems nowadays that why we didn't use machine learning methods, because that time when we published the results, our aim was to provide prediction methods which are very easy to apply. So in any program, you can calculate the parameters. So it should not be connected to R being able to use the predictions. And then we used the best performing prediction methods to prepare the soil hydraulic map for Europe in 3D, which means that we predicted the before mentioned soil hydraulic properties for 7 soil depths till 2 meters. And the input information to do these calculations was the soil grids. We used both the 250 meter resolution and the 1 kilometer resolution. The 7 soil depths means that it was like in soil grids 0 centimeter, 5 centimeter, 15, 30, 60, 100 and 200 centimeter. So these are the soil properties, the hydraulic properties that you can find in the EU soil hydrogrids database. This is the name, and what you have to be aware that the values are multiplied due to optimize the size of the files. And then we checked how good are these predictions, and it was very much challenging. So first let's see what is the performance on the test set, which means that in the test set we had real measured soil properties, so these were accurate. And then we applied the Pareto transfer functions. Then we calculated the root mean square error. These errors are, let's say, acceptable till now. Based on these soil properties, it is you cannot get much more better, let's say, much less uncertainty. Of course, in this database, we had a lot of different kind of soils from different climates. So, of course, other soil properties would influence the soil hydraulic properties, which would make it more precise, their predictions. But to stay at the reality, we use those soil properties which are usually available. So, for example, the clay mineralogy, for sure, would increase the accuracy, but since it is usually not available neither in the training dataset, we could not analyze its impact.
2 more minutes.
Okay, and then, so the most important, so how far you can get, that if we tested how it works when we use the soil grids database, which is already a predicted database because they had few thousand profiles, so then they use the prediction to get the spatial information, then you can see that the root mean square error is much worse compared to that when you had the measured soil properties. So it shows that there is a lot of room to improve this soil hydraulic data set, but we hope that it can be a step forward for different applications. And there are some warnings for when you use the data set, but maybe now I run out of time. So just to show that the database is freely available, both from our site and both from the site of the Joint Research Center. And just to show you fastly, I am not expert in drones, but in our institute, we have colleagues who are working with this equipment, and just fast show you what kind of equipment they use. And they are János and Mátyás, who are the experts on this field. Thank you.
Thank you very much. We have about half a minute for a quite quick question.
So one quick question.
She has a lot of very nice information on the slides, so we will share the slides. Huh? Yeah. Perhaps a quick question is, you have these soil profiles. Now, if you want to extrapolate to other areas, how do you use that PTFs?
So we do not use.
Is it on?
So what we did in for the soil grid, so we used a soil data set, which is already has a spatial area.
Yeah.
So it was the idea, because if we would use just the UHID data set, you have too few points.
Yeah.
So if you check the map, it is not
So it
possible.
covers whole Europe now.
It says it doesn't cover well Europe. It covers well certain places.
Okay. Okay. Yeah. Okay.
Mm.
Thank you very much. Okay. Thank you.
Thank you.
So our next speaker is Isabel Pedroso de Lima. She's from the University of Coimbra, Portugal. Let's see if I come up with it.
Well, good afternoon. Indeed, I'm coming from the University of Coimbra, and the main purpose for this presentation is to bring here some information on research that we are doing at our university, in particular at the Laboratory of Hydraulics, Water Resources and Environment. And I really hope that this PowerPoint decides to start.
Maybe you should close down this next time. There are too many open maybe. Yeah, close the first two.
Yeah, of course. Sorry. So the research in this case is on using infrared thermography towards optimizing water in irrigated agriculture. Now, as we all know, data limitations are often, well, which include, of course, a lot of measurement issues, are often pointed out as holding back our understanding of the hydrologic response, and that's the reason why, for many of us, we are trying to use a number of non-conventional methods that try to overcome some of those problems. One such, attempt is on using thermal infrared imagery to indirectly make a quantitative estimation of several hydrological processes. And of course, after all these talks on infrared thermography, I will just point out that this technique can record fast changes in temperature, and that indeed it has been showing being an effective, fast and accurate method of monitoring temperature. Now, at our lab, as I was saying, for already a number of years, that we have tried to develop and to validate thermal techniques for monitoring the soil surface. So I will quite briefly give you an overview of some of the applications that we tried to explore. For instance, on estimating shallow flow velocities, we have conducted both laboratory experiments and field experiments on comparing, for instance, which is the case for this image, thermal traces with dye tracing. We have tried to estimate soil surface micro-relief and reels. In this particular case, we were willing to visualize preferential flow paths and identifying micro-relief elements even in situations of non-bare soil, so when the soil was covered with for instance, mulch, and we have tried to do that with different coverage percentages of the soil. Our final aim was in this case to estimate a 3D model of the soil surface from temperature gradients, and you can see here some results, so some thermal images with increasing vegetation mulch cover, and on this right hand side a 3D model that we have obtained from thermograms. But indeed we were succeeding to at least understand a little bit what was going on below the cover, the mulch cover, although we could not have access to it directly. Another application was on mapping permeability and macroporosity. This is indeed some pictures from some exploratory work that at the time we were conducting in the lab to detect macroporosity. Later on, a number of field experiments and field work was conducted. The same with respect to mapping soil porosity, where indeed thermal images were able to identify different types of porosity in the soil. Now, with these and other applications as a background, we joined some colleagues from the Agriculture College from our town, so from the Polytechnic Institute of Coimbra, and we are now conducting, this is, I must stress, work in progress. We are now conducting work within a research project that is funded by the Portuguese Foundation for Science and Technology on modeling surface hydrologic processes based on infrared tomography at local and field scales. So our aim is really to develop infrared tomography-based tools for the analysis of the water distribution uniformity, say efficiency, in irrigated agricultural fields, of course with the aim at optimizing the use of water in agricultural systems. Our field experiments are being conducted in a nearby region. So, okay, Coimbra is located here. This is where we come from. We're really almost in the beginning of the last part of the Mondego basin. This is the drainage basin of a river that really starts and ends in Portugal, because, as you know, our major rivers start in Spain, but this one not. And it happens that in the lower part, the valley opens a bit, so we call it the Lower Mondego Valley, and there we have some 15,000 hectares of good agricultural land, where potentially irrigation can be conducted. From that, 12,500 hectares are presently being irrigated. The water is supplied by an irrigation canal, which has its intake in a dam that is actually in front of the city of Coimbra. Now, although the average annual rainfall for the catchment is around 900 millimeters, this downstream part is much drier, that's one thing. And the other thing is that in Portugal, sharing, of course, what is happening in the Iberian Peninsula and also in other countries in the Mediterranean region, the climate is characterized by strong seasonality, which means that during the whole summer, indeed, we have very, very scarce rainfall. So without irrigation, it's really impossible to grow a number of crops, and that is, of course, important for the region, for the farmers, for the development. Now, we have concentrated our experiments so far mainly on maize, because this is a dominant, say, crop in the area, and the delivery of water is done in a way that it is possible to irrigate by gravity almost everywhere where this crop is grown. There are some parts where the farmers use sprinkler irrigation, but mostly this is done by furrow irrigation, which means that the farmers have, well, they decide themselves when to irrigate, they decide how much to irrigate. So we all feel that indeed there is not so much efficiency sometimes in the use of water, and as you can understand, there is strong competition for water. I did not mention, but that irrigation canal, it delivers water for agriculture, but also for some paper industries in the area, and also for domestic supply in a city downstream of Coimbra. So our attempt was trying to evaluate the plant water status via its thermal reflectance to understand indeed what kind of differences we could find in the area that could somehow in the long run, as I was explaining earlier, result in a number of indications to the farmer has to improve their practices, their irrigation practices, towards, of course, improving water use, of course, but also their crop productivity, which is sometimes not very not satisfactory. So far, and in addition to other detailed data, we have been conducting infrared tomography ground measurements at the local and field scales, so for assessing the conditions of the canopy, of the leaf, of the soil, using both handheld cameras for the time being. So our main purpose is also to use UAS measurements, to conduct them with the drones, but the last cropping seasons we were unable to do that, so we only conducted the other types of measurements, which we have somehow complemented with processing of satellite-based images of the region, of the plot, actually, field plots. Now, crop grows quite a lot, so indeed it's not an easy task after a little while to take images from the canopy. We have to improvise some equipment, fixing the thermal camera to a mast and so on and so on. So we really hope that the drones can improve that type of acquisition of data, but I must admit that we are still in a very exploratory, say, stage with respect to this. We are really interested, of course, in what has been in what was shared here during these days, and in what is really one of the goals of this cost action. We are preparing ourselves to start pretty soon with a measurement campaign, so monitoring campaign, together with the acquisition of other types of data, but I don't have any kind of results to show here. As for satellite-based images, well, this is a real image. We were able to, of course, locate our experimental field. This is one example. We have downscaled it to 30 by 30 square meters pixels, and we were quite pleased in a way with the result, because comparing for a given date the measurements with the satellite, the measurements, the ground measurements, we were, even with the satellite data, we were able to identify, for instance, that information was giving indication that the water stress of the plants were increasing as we were moving away from the inlet point in the field. So this furrow irrigation allows that clearly, since it is almost all of the time differences in the amount of water that is applied in different parts of the field. So this was given, of course, by estimating crop water stress indicators for that. So we aim indeed at, as I was saying, complementing these two scales with information obtained with the drones. Most of all, to understand, that's what has been discussed here the whole time, to understand how to bridge between these different scales of observation. And, well, finally, that's the final goal, at contributing to using infrared tomography-based tools that use, indeed, non-invasive and non-destructive technology to achieving water management sustainability goals that are very, very important for us in the region. Thank you.
Thank you. Thank you very much. Questions for Isabel? Yes, Eyal? Come here, please.
Thank you for your presentation. One question and one comment. What kind of satellite sensor you used?
Landsat 8.
So you use only one band?
Yes, we did so far, yes.
Okay.
At least for exploring this type
but
of
didn't you say this is 30
relationships.
meter resolution, spatial
Well,
resolution?
with downscaling, we know that there is a lot of uncertainty, but because of the size of our experimental field, we brought it down to 30 meters resolution.
Okay, and a comment. I think you meant not thermal reflectance, but thermal emittance. You did measure, I think, reflectance. This was emittance, if I'm not mistaken.
Yeah, okay, probably. I'm sorry.
Yeah, just
Okay,
Small
I'll
comment,
check it
yeah.
out. Okay, thank you.
Thank you. Other questions? Isabel, I have a question that is about the use of the thermal data to calculate the stress. What kind of index was calculated exactly?
Okay, we used the crop water stress
Okay.
index
Okay.
for the handheld measurements,
Yeah.
and then the temperature vegetation dryness index
Okay. Yeah.
from the satellite-based
Yeah.
information.
Yeah. So is that a consistent relationship or every time you
Well,
want to calibrate?
at least in the qualitative terms, it was possible
Okay.
to see that they reacted, so they
Yeah.
showed sensitivity
Yeah.
to the information that we had by other ways, collecting other data in terms of water stress
Yeah.
in the area.
Yeah.
So I must say that we have, for instance, compared those, tried to establish a relation between those indices and crop productivity. We had
Okay.
information for that, so there was a good relation. In our experimental fields, we are not only applying, for instance, different types of maize, but we are also applying different amounts of irrigation. So we
okay.
kind of, I did not explain it fully, but we were controlling some
Yeah.
variables that could allow us to get a little bit confidence in the results.
Okay.
In any way, this is a work in progress.
Yeah,
I
very
want to
nice.
stress that again.
Yeah. Thank you. Other questions? You still have some
Okay,
time.
thank you.
If not, then thank you very
Thank
much.
you.
Yeah. So next presentation given by Carlos. Okay. Carlos Echeverri on the use of remote sensing soil moisture data in spatial temporal model calibration. He's from here. Yeah, he has the microphone.
Hello everybody, my name is Carlos Echeverria and I will talk about the use of remote sense soil moisture data in spatiotemporal model calibration for a Mediterranean catchment. ¿Se me escucha? As a quick introduction, I want to talk about the calibration of a hydrological model. We have two big approaches. The first one is mono-objective with just one objective function, and the second one is a multi-approach when we can use to evaluate two or more objective functions. And in this case, we use multi-objective calibration, including spatiotemporal data, and with spatiotemporal state variable is remote sense soil moisture. The objective of this research is the evaluation of the performance of hydrological model using a multi-objective algorithm, including remote sense soil moisture. And the projection is to use in engaged basins. To carry on our methodology, we use the hydrological model TETIS, including vegetation dynamic model. For the mono-objective calibration, we use the SEUA algorithm, and for the multi-objective configurations, we use the MOSEM UA algorithm. Our study area was the Upper Turia River watershed. It's located in Spain, occupying the Comunidad Valenciana, Castilla-La Mancha, and Aragon. This is the main characteristics of the basins. We have drainage length about 450 kilometers, an area of around 4,000 square kilometers. We use 93 temperature, evapotranspiration and rain gauge stations, and also we use 13 radiation stations. About the satellite data, we use the soil moisture maps covering the Iberian Peninsula with a daily temporal resolution, a temporal coverage of 5 years. This database was downscaling using the brightness temperature, land surface temperature, and NDVI. The spatial resolution is of 1 kilometer. That data is you can access for free by the SMOS BEC website. The BEC is a research institute located in Barcelona. And the new version also provides soil moisture estimation independently of cloud cover. About the methodology, we set up 3 configurations. The first one is a mono-objective configuration, considering as a main state variable the flow at the catchment outlet point. The objective function selected was the Klein-Gupta efficiency. We divided in 3 periods, warm-up period of 2 years, calibration and validation period of 3 years each one, and we evaluate 24 parameters, 9 hydrological and 15 vegetation parameters. In configuration 2, we select the MOSEM-UA algorithm. The main state variable is also the flow and the catchment outlet point, but we evaluate 2 objective functions. The first one is the same as the first configuration, and the second one is the balance error. The periods and the parameters are the same in the 3 configurations. Here, as I said recently, the parameters and the periods are the same. The objective function applied to the temporal state variable was the Klein-Gupta efficiency, and to the remote sense, with what is our spatio-temporal variable, we applied an index that we call a soil moisture estimator. The algorithm was the same, the MOSEM-UA. Before I continue, I want to explain quickly how we compose our function. The soil moisture estimator, it is a function to evaluate the performance of the simulated and observed soil moisture, composed by 2 parts. The first one is the KG index calculated in observed and simulate soil moisture pixel by pixel. And the second one is a metric based on the similarity between the 5 spatial principal components of simulate and observed soil moisture following the EOF methodology. Here we can see the formula that we apply. I don't want to explain the formula because it's too long, but I will continue. Results. The configuration 1, we established a convergence criteria. This is our convergence criteria, and we reached this convergence criteria after 1,325 iterations, and we got a KGE around 0.8. Now, in validation step, we got an index around 0.1. As you can see, a big reduction. In the second configuration, we set up our algorithm with an initial population of 1,000 points. We divided in 50 complexes of 2 points per complex, and we decide 5 new candidates per complex. And we put also 150 iterations. After more or less 40,000 simulations, we got 97 candidate solutions, and from these candidate solutions, 6 are parts of the Pareto front, as we can see in this picture. This is the Pareto front, and these are the solutions composing the Pareto front. So, what was the chosen candidate solution? The criteria was to choose the candidate solution who has the best performance in validation step. So we got these results in calibration, a KGE of 0.77 and a balance error around 9%. In validation, we got a KG around 0.2 and a balance error about 37%. Now, finally, the third configuration, the algorithm was set up of the same of the second configuration, but finally, after 40,000 simulations, we got 59 candidate solutions, and from these 59, 4 are part of the Pareto front, as we can see in the next picture. This is our candidate solution, and this is the Pareto front. The criteria to choose the solution was the same as the second configuration. The solution who has the best performance in the validation step. And we obtained these results: a KG of 0.37 and a soil moisture estimator 0.58. Now, validation, this is the interesting part. We got a KG around 0.623 and the soil moisture estimator with a little reduction of 0.53. So, in conclusion, calibration multi-approach, even including just temporal variables, is possible to improve the performance of the model. But multi-approach calibration, including spatial-temporal information, improve the performance even further. So even including spatial pattern implied less reduction in the temporal estimator, the spatial-temporal estimator presented just a little reduction in validation. We did a kind of ranking between the 3 configuration solutions. In calibration, the best solution was the first configuration. In the second place, we have the second configuration, and in the third place, the third configuration. But in validation, we have the order changed. The first configuration is in the first place, the second configuration kept in the second place, and the first passed to the third place. But as we are scientists and we prefer numbers, in my case I prefer numbers, I prepare a little summary to explain. The interesting part of this table is the result variations. From calibration to validation, we have a reduction of 0.7. Here we have a reduction in one variable of 0.55, and the balance error was an increasing of 28%. And in the configuration 3, we have a 0 point, the variation between calibration and validation in the KGE, and in the soil moisture estimator, we have a reduction of 0.015. And that's it for me. Thank you very much for your attention.
Thank you very much, Carlos, for your very nice presentation. Are there some questions?
Thank you. There are a couple of questions that I would like to ask. One is how many calibration did you run, and the error and the estimated error coefficients are mean values of the calibrations, or are just one run at the final table in this one? This is one run, or it's a summary of several runs?
The summary
is the mean?
Is the summary from this one. After 40,000 simulations,
Mm-hmm.
we chose what we think are the best results.
Mm-hmm.
And
So it's one value. It's just one calibration versus compared to each of the other. Okay. So it's the best calibration for each of the methodology applied. Okay. this is something, even if I think it's interesting to explore the variability of the parameters and the impact of this variability, this is something we can discuss later. The second question that is also a key question is how, I don't have the answer, so I'll try to stimulate the discussion in this. How can we use such a detailed amount of information that we can obtain from UAS in the calibration and in the use of this kind of models? Are these models suitable to implement this kind of information, or we should think about different models? So what are the problems that you see right now? If somebody comes to you tomorrow and says, okay, I have multi-temporal images of soil moisture data at the resolution of 50 centimeters. Can you take advantage of this information?
Depends of what you want to analyze. In our case, we chose this data because it's the closer to our model resolution. This is our criteria. But if you are modeling with a smaller, this is the idea, to use drones to estimate to improve the resolution, and to use, if you improve the resolution, you will get better results. I answered your question, sorry.
The opinions are different.
Yes, yes.
I think it's a real, that is a real challenge. Yeah, perhaps I'm here for general discussion to think about it. If you have much more data in terms of order of magnitude more, does it help you to improve your modeling? That's something we have to, I mean, you can actually do that.
Yes,
Somehow, if you use a small data, of course, it's very close, but the drones are 3 orders of magnitude finer, or 4. So that can be something.
I would prefer to use with better resolution, but
Yeah.
I use what I have, so
Yeah.
it's all what can I do.
I think added question to what has been already asked is about the parameters, the physical meaning of the parameters. Do you actually control the physical meaning, or do you just give a range and let the algorithm to scramble around that?
No. I put the limit to search the best parameters. I read a little bit or
from literature. Or
from the
your
literature,
previous-
and the minimum and maximum parameters
Okay.
depends of the kind of soil. So
Okay. So if I remember well, you had 5 parameters for the soil and 9 for vegetation, or something like that? Or different?
in my case,
Yeah.
my watershed has 5 kind of
5
soil
kinds of
use,
Okay.
and I calibrated 3 vegetation parameters in each kind of soil.
Okay. So if you use the pedal transfer function for Brigitta, would that improve your?
It's a nice idea.
Okay. We have to stimulate the discussion, right?
Yes.
Okay. Yeah. Thank you very much. Yeah.
To you.
Very nice. Let's see. Okay. The next presenter is myself. So I'm sorry for not being able to put it into the template. So every time I have to change a lot of things. So my name is Bob Su. From the University of Twente. We are working with a large group of colleagues from my institute, from Chinese Academy of Sciences, but also in collaboration with ECMWF, with Paolo Ferrazzoli, Mike Schwankel on the remote sensing part, and Jan Kerr, and Andreas Colliander on a new satellite. So the idea of this presentation is just to give you a quick overview about what we are doing in terms of soil moisture, but also brightness temperature. Since 2006, we have been starting to establish so-called soil moisture, soil temperature networks. The idea is to have a really in-situ calibration sites that we can always go there. We have continuous data. So we have in the Netherlands, here in Twente soil moisture and soil temperature network, but also on the Tibetan Plateau, we have actually 3 across the different climate zones, from humid to semi-arid to desert area, where we have this measurement. For each of these sites, we have 20 profiles separated into area of about 40 by 50 square kilometers, so that you can directly compare with satellite data. So that's the idea. The network was supported by different projects, but we maintain it. We intend to maintain it into the future, so as to create some kind of a climate quality data set. Now the measurement itself, if you look at the surface measurement, the 5 centimeter measurement with the 20 profiles, actually tells you a lot of information about the soil itself and about the, say, the meteorological conditions. What you see here is that when it has a jump, you notice that there's a precipitation event. And then if you look at all the 20 curves here, meaning the kind of phenomena here is larger scale, covering the whole area because they are very, very much separated. But then if you look at the individual curves, it tells you actually about the soil texture information here. So it gives you a lot of information about the soil texture and what is influencing the soil moisture pattern. And then if you look at the diurnal cycle, it tells you the kind of evaporation. And if you extract the information from this data, you should be able to model evaporation very well. And here, basically, the reduction of soil moisture due to evaporation. So this gives you actually a lot of information that you can use both in modeling and in remote sensing to see, okay, what is really measured. And that was also motivation that we put this network together so that we can always look at what's happening there. So the first thing we did was basically put up a paper describing the network. It's called Tibet OPS. The data is publicly available. And what we did was actually to look at the available satellite data at that moment, where we looked at basically the AMSAR-E data, the ASCAT data, large scale satellite data, and you see they have a kind of all kinds of differences, and particularly in the winter period, where you have typically largest uncertainty, but then it depends on your application. It can be quite critical if you're looking at the permafrost type of things. So that's one of those applications. This is also used actually to look at the uncertainties in the different data set. Recently, beginning of last year, we have added a so-called radiometer, Albara, which is a 3-meter hole, and measure L-band brightness temperature in situ. The instrument is owned by the European Space Agency, but we are allowed to use it till its lifetime. And the site we have in the eastern part, in the Machi site, is we have a micrometeorological station measure all the fluxes and meteorology. And here we have the radiometer, which looks into the sky and then do scanning in different angles automatically every half an hour. And then we have a meteorological station. We have a cosmic ray probe to measure integrated soil moisture. And in the ground, we have different soil moisture profiles. So in principle, for this site, you can do modeling. You can check the algorithms. You can also look at the different type of retrieval results here. What we do in situ is basically we measure all the different soil properties, thermal and hydrological properties. We put up a very dense measurement network in terms of profile to see from a radiator transfer point of view to know exactly what is the effective temperature. And we calibrate a lot of the soil hydraulic and thermal properties also. So the questions we asked was basically, first, how good is the satellite signal? If you have satellite signal, satellite observation, how good is that observation? Now, if you use that observation to do a retrieval, how good is that retrieval? And then next is, okay, if you have a pixel scale type of measurement, how good is that in terms of spatial temporal representativities for that area. So these are the questions that we thought could be quite interesting. Now, to answer those questions, first thing is that if you have the measurement, in this case for the SMAP, and we can directly compare to the measurement of the Albara measurement, both for the horizontal and for the vertical polarization. And in this case, you can be sure, okay, they are, of course, they have differences because the areas are different, because sensors are slightly different. But still, when you look at the seasonal scale, they seem quite consistent. The same is also for the SMAP data. That's the NASA satellite, which is still closer to the in situ observation with less scatters. Now, when we put all those data together, we can then examine if we can use the data simultaneously to do both the forward modeling, but also do the retrieval. Now, in terms of the modeling itself, the first thing you need to basically explain is if you have the in situ measurement from the radiometer, the Albara, and if you have a satellite measurement, you first need to explain if they are the same. And in this case, if you look at the beginning, this is from 2006, the 1st of January, till the day 40 or so, they were quite consistent. That is because the Tibetan plateau was frozen, and they are looking at the dry soil, so it's kind of uniform. They have exactly the same kind of signature. But starting from the day 40, you notice that they start to divert from each other. And this is actually kind of a special variability where the certain part start to melt because of the temperature change. And if we check the temperature at the 5 centimeters, it is indeed coming to very close to 0 degree, whereas on the surface, the part of the soil is or the soil in that case. And from that, we calculate the effective temperature. It is also increases. So this is part of the signal that need to be explained. Now, in order to actually to understand the signal, what we did is we coupled typically remote sensing people would use a radiator transfer model to do the modeling part. But then the problem is that you do not know what is input parameter into that model. So what we did was couple a land surface model used by ECMWF for the NSAP with a radiator transfer model. So given meteorological information, we would be able to simulate a signal, observe the signal by the sensor. So the way of coupling is you have the land surface model or your hydrological model, you have a radiator transfer model, and the different part of emissivity and the temperature part, they are coupled into a coupled system so that you can do the simulation. And with that, then you can do different type of experiment. Say I use soil moisture from the first layer. I can say the first layer is a little bit thinner, not 10 centimeter, but 5 centimeter, or even thinner, so we can simulate all these different type of profile. And what you see here is that forward simulation with respect to the observation by the Albara radiometer. And you see that if you use the normal configuration, use top 10 centimeter as your model input, you will never be able to match what is observed. You can have maybe something like 20, 30 Kelvin differences, and this is very big difference in terms of brightness temperature. So only when you decrease the surface layer into 2 centimeters, you will be able to come to close to match whole and water. But still, you notice there are differences in different instances. So from this exercise, we thought it is kind of essential if you want to explain the kind of brightness temperature and the dynamics of that, you need to have a coupled system to actually measure how and what is going on. So another part of the work that related to this is that typically the model we use are a little bit simple, 4 layers or 5 layers whatsoever. And what we want to do is we want to have a kind of numerical model to be able to measure, to be able to simulate the complete surface atmospheric interaction. And this model is called Stamius Ijie Zeng. He was at the kickoff meeting, and actually he developed model during his PhD thesis. Currently, the model works also for permafrost, and the evaporation vegetation part is also added to that. Our idea is that this should form a component in the kind of Earth system model, so that we can simulate satellite observation, but we can also do all kinds of scenario simulation. What the model behind this, I thought that today we haven't seen a lot of equations, so I just put up one slide to show the equation. What we have is we have the soil water transport, we have a soil heat transport, plus soil dry air transport. If you do not have this part, typically in hydros, for example, you do not have this part. And you cannot model very extreme dry situation or frozen situation effectively. If you use hydros to a desert area, probably it will fail. The evaporation will be not correct. And if you also want to model gas transport, CO2 or whatever gas transport here, that's also part that is quite important. So a quick example of this is that you can simulate both the soil ice content and the soil water content, and also the freezing dynamics in the soil profile itself. So it provides you some kind of numerical method to do that. And what you see here is that typically we would assume that when it is frozen, there's no evaporation, but this is not the case, actually. And if you look at the simulation, the evaporation can be actually quite high in winter period. It can be 0.5 millimeter, although it is low compared to during summer period, but on a climate scale, that is still quite important. So in conclusion, I would say process understanding based on measurements and modeling is of primary importance if you want to really understand what is going on. And the calibration validation is always needed to ensure the stability and the truthiness of the observation and the retrieval, and in particular for climate change, climate-related studies. Spatial scaling remains a challenge, and perhaps here we could use UAS to scale from the point measurement to a grid scale so that we can develop some kind of a new type of methodologies for that. And finally, I thought the modeling and the data simulation remains indispensable in understanding the efficient use of observation and retrievals. The work presented by Carlos and a few others, I thought that kind of interesting. Perhaps we can get a work group together to see, okay, we have all this measurement of surface temperature, soil moisture, how do we actually put that into hydrological modeling to improve the modeling itself? So that's all from my point of view. Do you have questions?
Thank you for your presentation. I'd like to ask you if I understood correctly. You are speaking about the surface moisture.
Yeah.
Okay. So I have a question, which is actually is very important, and I don't see it in all the modeling. Soil moisture content is heavily dependent on the mineralogy of the soil. How this is taking into account with all the modeling and also with selecting those stations global wide?
No, I think from the modeling point of view, perhaps the most important part is what Brigitta presented. So the hydraulic parameters in that case. And in most models, they do not use the mineralogy as an input. They use some kind of porosity, wilting point, field capacity, some kind of pedal transfer functions for that.
I see. So
there's a gap between what you do and what the hydrological or land surface modeling people do.
Okay.
It could be interesting actually trying to bridge that part.
And how did you actually select the stations global wide to present or to have some global variation of the soil over the board? What was the main idea?
Yeah, I mean, from the SMAP point of view, they were looking at areas that they have already some kind of stations. Like in the US, you have a lot of stations. What we did was we looked at basically the scale of the observation about 20, 30 kilometers squared. So we looked at, we said, okay, we would like to select a representative area. So if it's too heterogeneous, it doesn't work. So
But
yeah.
I saw that it was also in the always in the north hemisphere, not in the south hemisphere.
We have one station in Kenya, but it's kind of difficult sometimes. Last year we couldn't access it because of the election. And this year it was also a lot of challenge to get him because they changed management, and then we had to pay an entrance fee into the park. It's a very nice station. I would recommend everybody to go there, but I mean, there are all the kind of local challenges. If it's not in the park, you put it outside, everything will be stolen, including plastic, whatever.
I know that from South Africa.
Yeah, it's kind of pragmatic,
Trade-off.
based on feasibility and based on what you desire.
Okay, thank you very much.
Thank you. So I guess we have to move forward, but okay, Yunus, last question.
Actually, it's not really a question, it's a comment, because sometimes in this room, the meaning of soil comes into play. So depending on the problem and the type of a model that you use, the meaning of soil may be changed a little bit. You are talking about a physical meaning of soil, but I think that in the model that Bob is using, we need a more functional meaning of soil, because the parameters are not the water retention and hydraulic conductivity that I agree are strongly dependent on mineralogy, maybe the clay content. But if we use such a model in a relatively large scale, we are talking about a functional a meaning of soil in terms of fill capacity. Fill capacity is not a soil property. It's a process-dependent property because it depends on the drainage of a soil. And drainage is a process. It's not an inherent soil property. So even when we use drones to retrieve soil properties, we should keep in mind which kind of a model will exploit the parameter we are measuring. Now, this is the comment.
Okay, thank you. Just a quick addition to that is in the radiator transfer part, we do use clay content and texture as the input to convert soil moisture into dielectric constant. So kind of dielectric mixing modeling. You need that to be able to simulate the emissivity part of that. Okay, thank you. Let's move to the next presentation. Antonino, you are doing that? Okay. From Antonino Martes from University of Palermo. He was the chair of the previous session. So his talk is about surface and surface soil water content mapping using thermal images. Please.
Thank you for your introduction. First of all, I have to say that this presentation is from me and from Giuseppe Cirauro from University of Palermo. We are two cost members, but the results we are going to see and the applications are also from other researchers from the same university, Fulvio Capodici, Mario Minacapilli, Carmelo Cammalleri, and Goffredo La Loggia, among others. So I'm going to talk about two techniques employing thermal images to estimate soil water content and to highlight limits and advantages of these two techniques. First of all, I have to say that we have some proximity sensing facilities at university, and we started 10 years ago with the balloon, with a thermal camera and a multispectral camera. Then we had also a sort of cable carrying instruments above it, and also tripods. And only recently, in the last 4 or 5 years, we bought also drones. These are two drones that are available at the university. The one we pilot is this one. It has 4 arms with is a counter-rotating helix, and it carries about 9 kilogram for let's say 10 minutes. And above these drones, we have installed the thermal camera and a multispectral camera that is the Ricola one we have seen today, set up with 24 bands. Okay, we have several methods for calculating soil water content, for retrieval soil water content. Some use microwaves, active and passive. We are going to put our attention of the ones using thermal and optical images. The first one is the triangle method, is from Carlson, and the second one is thermal inertia from Xue Cracknell in 1995. Even though first research on this issue began with Watson with the landing on the moon. And we have the first one, so it's thermal inertia. And I have reported a very short theoretical background. We are going to simulate the thermal, the temperature behavior within the soil. This is how the temperature change with depth in the night time, and when the temperature reaches the minimum. Again. And this second one is the maximum temperature, that is a couple of hours after midday, and it decays exponential to the same value, or almost the same value. And the thermal behavior in time at the surface and with depth, with the peak that is moving forward, and also the amplitude of the temperature that is smaller with depth. So if we use the thermal diffusion equation, we apply some boundary condition and initial condition, we can obtain a relationship like this. And within this relationship, we have the thermal inertia, that is this terms here, this term here, the P. And in order to calculate the thermal inertia, we need the 2 thermographies to delete this term, that is the daily average temperature, and also some visible near-infrared image to calculate the albedo. Here we have some results. Is the thermal inertia for the application of this technique with the 2 different models to take into account the phase difference. The one is from Xue Cracknell, that is straightforward but is a simplified model, and the other one need 3 thermographies, that is from Sobrino, from University of Valencia, and the data has been taken in barracks in the 2014, is the reflex campaign. And so we have the thermal inertia and the soil water content with 2 different techniques. Okay, if we use much more detailed images in terms of spatial resolution, things get more complicated, because you will be able to see the shadows of the trees, no? And these shadows are going to change during the day, and we have seen that we need 2 thermographies, so this shadow have a different position during the day into the 2 images, and also is clearly visible the vegetation, and the vegetation is another factor limiting the application of this methodology. That's because there is an hypothesis within the method that is a linear proportionality between the net radiation minus latent minus the sensible heat flux with the soil temperature within 1 day of acquisition. And anyway, if you let's say, mask out some pixel, you can obtain a proxy of thermal inertia, that is the parent thermal inertia, and then you can convert this quantity in a soil water content. This soil water content can be can characterize only bare soil or at most sparsely vegetated pixels. And it depends on the soil porosity and soil texture that have been accounted within the model. And if we use the first order approximation of the temperature equation, the solution is straightforward. Otherwise, if we would like to describe better the temperature behavior of the soil within the day, we need to use the second order approximation, and the solution is not straightforward, is an iterative solution. And we need to at least 2 thermal images acquired in suitable moments of the day. And the hypothesis is that the thermal diffusivity does not vary with the soil depth, and the soil water content that we are going to obtain is representative of that part of the soil where we have soil temperature oscillation during the day. Okay, so even if land surface temperature is a skin temperature, actually this value is influenced by thermal properties. And thermal properties within thermal inertia are the thermal conductivity and the specific capacity and the density of the soil. And thus it depends of the part of the soil where you have the oscillation of temperature during the day. The second method is the triangle method. This method comes from this background, and we know that the difference of temperature between canopy and air is given by this complicated equation. Within this equation, we have the stomata resistance and the leaf area index. And if we put in a scatter plot the leaf area index versus this difference of temperature, pixel, we're going to assume this kind of shape, and with the very high leaf area index we have transpiration, with very low leaf area index we have just evaporation, and there are 2 boundaries, 2 edges where we have the maximum of transpiration and evaporation, and the minimum transpiration and evaporation. These are called the wet and the dry age. So the idea is to put in a plot, in a scatter plot, air temperature minus canopy temperature and leaf area index, and then you find the position of each pixel and you retrieve in some way the soil water content. Actually, this method can be applied also in a more simple way, more operational way, using not leaf area index but other indexes like the NDVI, or not the difference of temperature but just the land surface temperature. And you obtain something like this. So if you want to, we have very fast. If you want to apply this method on a small area, then maybe a solution is to look at the multi-temporality of the data. And if you look at the multi-temporality, the pixels are going to move like this with the season. Okay? And it's not simple to define which are the dry and the wet age. And if we select these pixels, we see that in time they change, they occur in different months of the year depending on the year. Okay, and here we can see clearly the phenological behavior of the vegetation. So it is more complicated if we take into account the multi-temporality of the vegetation. And Actually, there are other factors influencing the soil water content. One of these factors, for example, is the closure of the stomata due to the solar radiation. And within the same scatter plot, this pixel take this position. It's not uniform at all. And not only the solar radiation influence that position, also the air temperature, for example, or the concentration of carbon dioxide, for example. So we have advantages and disadvantages as well, and we need just two temperatures. One is thermal images, another is air temperature. The empirical approach is straightforward, and you obtain the soil water content of the root zone of the soil. And there are several limits if you would like to apply multi-temporality. And here we can see the comparison between the two methods. So the first one is applicable to bare soil, while the other one to vegetation, to thermal acquisition versus one, and the different representativeness of the soil within the... That's all. So thank you very much for listening.
Thank you very much. A lot of nice data. Yeah. Okay, questions? Yes, Salvatore? Please.
Okay. Antonino, thank you for your presentation. I haven't seen a comparison with the ground data, considering that you have a good resolution to make a comparison. Do you have any?
Yes, we have some on different projects. For example, the thermal inertia method works very well on bare soil, and is going to fail when the vegetation cover is higher, let's say about 30% of vegetation cover. Triangle method, we have also some data for the triangle method. In that case, it worked well over a large area with the larger pixel from satellite images. When you look at images from drone, you have to take into account the multi-temporality, and then we still have a lot of problems, and maybe the index is more an index of stress of vegetation, a part also of water stress of vegetation, but not soil water content. Absolutely, soil water content is more an index of vegetation stress.
No, I think what we need to do is actually put all the different studies together, the one presented by Isabel, by you, and by Jesper. I mean, several of these actually experiments touch upon thermal observation, soil moisture, evaporation. Perhaps we should coordinate a little bit, say, okay, if you have a different measurement for the site, you play different method. What is really compared to some flux measurement, ID covariance? I mean, for barracks, you have a lot of measurement. We could learn a lot of new things given the kind of availability of data, because typically hydrological modeling, I guess Felix would agree with me, is typically data poor exercise, because you have some rainfall data and a runoff measurement somewhere. You don't know the spatial distribution. No, you have a temperature, you have soil moisture, colors show that. Now, if you try to model those things, do you actually get new insight into the system?
Could I add the consideration? The soil water content we are looking at actually is different.
Yeah, sure.
Because with thermal inertia, you look at soil water content of the part of soil where the temperature changes during the day. With the triangle method, you look at the root zone, so is water available to the plant. And with the radar data, you are looking at water that is able to change direction, to orient the pole. Okay, So we look at different kind of water, referring to different depth as well, and this depth is variable in space.
Yeah.
So I cannot say this is a soil water content of the first, I don't know, 30 centimeters. It's 30 centimeters in one place, and
Giuseppe, yeah.
Just comment. The experiment we did with a very high resolution for the soil moisture is located in our experimental field where we have eddy covariance, we have subflow, we have TDR, so it's fully equipped.
Okay.
It was used also for a previous campaign in a former cost project some
Okay,
years
yeah.
ago. Okay.
Thanks a lot. In interest of time, we would like to move to the next two talks, and we leave some of these questions to discussion for tomorrow working group discussion. Okay.
thank you very much.
Yeah. So let's. Next talk is going to be given by Flavia Taro from University of Tuscia, and now we move to a different topic. We move to stream flow and flow velocities in the last two talks. Please.
Thank you, Bob, and good afternoon, everyone. So my name is Flavia Tauro, and I'm from University of Tuscia. The research I'm going to present here today is related to working group 4. So stream flow measurements from drones, and the results I'm going to present today are from me and some other colleagues at University of Tuscia, including Professor Salvatore Grimaldi, Andrea Petroselli. I don't know if you know them, but just wanted to thank them. Oh, sorry. Okay, so this is the actual title of my presentation, and a little bit of a scheme. So to motivate and to introduce a little bit my research, I would like to start by mentioning a recent survey that was administered to the hydrological community and whose results were presented in a recent article by Theresa Bloom et al. So the objective of the survey was to ask hydrologists what they think the most urgent needs for hydrological research are. So it turns out that how do I, is there a laser pointer? Oh, okay. Thank you. So it turned out that the most urgent needs highlighted by the hydrological community were that new measurement techniques and equipment are needed, and that more field measurements and monitoring are needed with respect to modeling. One of the greatest challenges that was highlighted by this paper was the maintenance of monitoring networks that are apparently the bottleneck to the advancement of our comprehension of hydrological processes. And here is an example of water gauges in Germany, and you can clearly see that from the end of the 90s, the number of water gauges consistently decreased, and this means that we are currently facing a critical situation where we have limited spatial and time coverage. We deal with expensive equipment, such as traditional monitoring stations, that are also very costly to maintain. Okay, so some of the people in this room have tried to address this issue, and I'm referring to Salvatore and Giuseppe and Nino and some other researchers that together with me made up a working group. This is a working group of the International Association of Hydrological Sciences, and it's called MOXIE, Measurements and Observations in the 21st Century, that tries to address the dearth of monitoring stations and affordable monitoring stations by resorting to multidisciplinarity, innovation, and affordable solutions. So we're basically trying to involve all the hydrologists that build their own sensors using cheap material and also use smart or opportunistic data in order to come up with hydrological observations. And please take a look at our paper that just recently came out in HSJ. Okay, so as I mentioned earlier, the research I'm going to present here deals with stream flow observations. So stream flow is currently measured by using what I would call in the rest of the presentation traditional equipment. So mostly point-wise, so mostly equipment that leads us to point-wise observations at selected cross-sections, invasive sensors that need to be deployed into the current, expensive sensors, and this is the reasons why. These are the reasons why measurement campaigns are rare. So when we want to come up with stream flow observations, we are facing several challenges, and I will be listing some of them. So the first one is that if we want to get stream flow observations, we may get information on flowing rills, streams, or large-scale rivers. So we're looking at something that may occur at very diverse spatial scales. Also, stream flow observations may involve accessing difficult environments, like the ones that I reported in the pictures, that may be risky for operators and sensors. And even if this may look at a not very relevant problem, this is actually very important if we want to have data during floods. So we end up having no data during floods. And the other thing is that we are also looking at something that may occur very fastly in time. So it may be difficult to accurately describe the phenomenon by using traditional equipment. Okay, so what I did with what I'm doing actually with my research is trying to merge optic technology and image analysis in order to come up with easier and potentially more refined from a space and time point of view stream flow observations. So here is just a cartoon of like the objective of my research is. Okay, so why images? So images offers, as you mostly know, offer several advantages with respect to traditional equipment. So firstly, we can look at something that occurs at very diverse scales, as I mentioned earlier. We do not need to deploy sensors in the current. Also, we are not going to get point-wise observations, but we end up having maps. Okay, so here is the standard procedure I follow in order to get actual stream flow data from images. So to start with, I record videos rather than single images. So, sorry, I didn't do anything. Okay, so I extract frames from videos. I remove lens distortions. So I call this camera calibration. If the camera axis is not orthogonal to the water surface, I orthorectify images. Then I assign a metric dimension to pixels, and this is what I call the frame calibration. And then I enhance images in order to highlight important features that I use to extract actual stream flow data. Okay, so how do I get velocities out of images? I apply some velocimetry algorithms, and some of you may be aware of them already. So one of them is large-scale particle image velocimetry. This is a high-speed cross-correlation algorithm, and it's very simple. We basically divide, we actually overlay a grid over an image, and each cell in image 1 is cross-correlated to a search area in image 2, And the location of the highest value of the cross-correlation coefficient gives us a displacement vector. We already know the frame acquisition frequency, so that in the end we get a velocity vector. Here is another a velocimetry algorithm that is called the particle tracking velocimetry, and it's very similar to LSPAV, but it works in 2 steps. So in the first step we detect features or particles in image 1, and in the second stage we go look for the particle in frame 2 by using a variety of algorithms, from cross-correlation to some other options. Of course, these are not the only velocimetry algorithms that can be applied. Actually, I'm proposing a modified version of PTV, but I'm not presenting this today, so please refer to a recent paper in WRR if you want to know more about it. Okay, so here is the setup I follow when I take streamflow measurements with a drone. So this is the drone. I typically use very cheap platforms, like commercial ones. The only feature is that the camera has its axis orthogonal to the water surface, and the drone hovers, so its station keeps above the region of interest, so that we end up having a video with a consistent field of view in order to apply the velocimetry algorithms. So at the same time, we deploy tracers onto the water surface. Of course, we don't have to deploy people into the river. This is just a cartoon. And according to the type of velocimetry algorithm we apply, it is not necessary to deploy tracers. So this depends on the appearance of the water surface, on illumination conditions, and some other factors. Okay. So I've applied this methodology in a number of environments. Before going on site, I did an outdoor feasibility assessment where I hovered the platform above a large-scale grid, and I evaluated how much the field of view was changing. And it turned out that these changes were compatible with the surface flow measurements we are going to get from actual experiments. So here is surface flow velocity map obtained in a mountainous stream in the Italian Alps. So this map here was entirely reconstructed from images taken from a drone, and here you can see cross-sectional velocities along these green, red, and blue lines. So basically, this is how the whole procedure works. Okay, so this is mostly what I wanted to present today. So of course, I'm very happy to be part of this cost action. I think that UAVs can have a great potential for streamflow observations. Of course, low-cost platforms can be a bit tricky. We need to work a lot more on image processing to get reliable data. I've not mentioned earlier that an issue here could be the stability of the platform. Stability is pretty good, as Shursho was mentioning earlier, but wind effects may be challenging. So there are some algorithms that allows us to create a sequence of consistent field of view images. So of course, if we go with cheaper platforms, we have to work a lot more on the post-processing. Another nice thing that we would like to work on, and I share this idea with Salvatore and Giuseppe, is also trying to get actual discharge data from drones. And in order to do that, of course, we need to work together with the other section of Working Group 4, that is on river morphology in order to complement morphological data with the actual stream flow observations. And I would like to thank you for your attention.
Okay, thank you very much. Questions for Floria? Yes, Felix, come here, please.
Nice presentation, thank you. We just started experimental basin in an ephemeral river, and we have in the ephemeral river a flow gauge station, and the problem with ephemeral river is that when flow comes, there is a high probability that the sensor is not working, and you didn't know until the flow. The advantage is we know the cross-section, because in your problem probably you need to know the cross-section of the river. In a ephemeral river, it's easy to know. But my question is, in our case, we will need to fly the drone during the rain. There is some difficulties to take measurement of velocity in a rainy day, or doesn't matter?
Okay, so this is actually a problem we had with some during some experiments in my university. So there are some drones that are specifically designed, and you could purchase them on the market, and they are able to fly while it's raining. Another option we actually built a device that can be mounted on the drone and allows it to fly while it's raining. Of course, this does not completely ease you from challenges, because another important effect you will have is the impact of raindrops on the water surface. So this is something I'm actually working on. We have another permanent, like a rain gauge, gauge cam station that it's permanent on the Tiber River, and I have a very large data set, of course taken also while it's raining, and this is something I'm actually trying to work on from an image processing point of view, trying to remove the noise introduced by raindrops in order to recover stream flow velocity in challenging conditions.
Thank you. Yeah.
Yeah, of course. Yeah, I've worked with the, you mean rainfall simulators? Rainfall simulators, yeah, I work with them, and yeah, this could be another option, but of course, I mean, we also have images of natural rain, so it could be challenging to base your algorithms on something that is artificial. But of course, this maybe, yeah, you could start from that. But yeah, the data set, the images I have are from a permanent station, so this is already an ideal condition since your platform is not moving, so at least you have a consistent field of view and mostly constant illumination conditions, so it's already something that simplifies things.
Okay, thank you. I have a very quick question. Your title was flow measurement, and you showed all the velocity measurement. So
Yeah.
don't we need a boat or so somewhere
Yeah.
on the river where Peter was showing this, or what is your solution?
Yeah.
Do you have already a rating curve?
No, I don't have a rating curve. This is something that we would like to work on, and already from several years, I would say. Of course, it's challenging. So as of now, I'm aware of some other researchers that have obtained depth measurements from drones, but this, of course, only works in case of very shallow depths or very transparent water. So it's not like a representative universal application. And I never measured discharge from a drone, from images taken from a drone, but I still believe that mapping surface flow velocity may be important for modeling a lot of processes, like, I don't know, for instance, erosion and stuff like that.
Okay, thank you very much. Maybe we will hear a little bit from Salvatore, you are also talking about the flow here. No, we are
On
all
time?
right, we are already on time. we
No,
still
no.
have half an hour.
Okay, okay. I will try to be short. Where's the pointer? And I wouldn't take. It wouldn't take any longer, so I will go to the conclusion. This is just a piece of the activities that we are carrying out in our department. And I decided to bring this work in and to present it during the workshop because I wanted to provide complementary information to the results that just described by Flavia. The topic is about monitoring essentially the surface flow velocity using specifically PTV methodology. So we have seen most of the technical details of this kind of application have been already described by Flavia. So this is very beneficial for my presentation. Probably what we do not fully know as an audience is the fact that the surface flow velocity it may be extremely useful also to get information about the flow discharge. And I tell you why. Because in the reality, there is a huge amount of literature that is studying the flow velocity profile within the cross-section. And the theory that these people have developed clearly state that there is a clear and well-defined linear relationship between the mean velocity over the vertical, so over along the depth of the cross-section, and the flow velocity at the surface. So in the reality, and the proportionality factor is about 0.7, 0.75. So we know how to use these measurements. And in fact, there are several commercial devices like radar pointers that measure only the surface velocity. And just using this information, they provide you discharge measurements. And so this kind of information is already developed in an engineering software. So more specifically, coming to the topic of this talk, we have been focusing on the setting of the method and the parameter setting for different application. So in order to do that, we have been studying by numerical simulation different configuration, using artificial background, using natural background, using particles with different densities, and in order to explore the required density of particles, of floating particles, exploring the color of these particles, the effect of color distribution and the presence of noise and a random variability of the color and the signal of each of these particles. And these analyses have been are summarized in a number of graphs. Here I've just reported a few of them. And in particular, we actually started exploring the impact on different simulation of, for instance, the particle displacement that actually play a role. And here, when we talk about ideal configuration, we talk of a case study where we have a uniform background with floating particles moving. And in here, we don't see any significant impact in the relative error of this technique applied to this kind of configuration, while some differences are actually observed in the variance of the measured velocity when moving from from slow displacement up to a larger displacement. And apparently the displacement is a key factor that we need to know in advance somewhat in order to understand what it should be the particle size that has to be used in a specific configuration. It is affecting the measure and more mostly the variability of the measure up to a certain point, and after this point, essentially after the 2.5 is the ratio between the displacement and the floating particle diameter. There is less variability, but this parameter is less effective. It is less effective for our measurements. So what is more effective is essentially the seeding density. Let's focus more specifically on the real configuration where we have a more realistic numerical simulation with a real background, with particles that are actually associated with random distribution of colors, but in this case uniform, randomly distributed in space and moving with a constant velocity. We can therefore quantify clearly the error associated to each measure, and we can clearly identify that there is a minimum density required to obtain the good performances of this kind of method. And of course, this is due to the fact that we need a fairly good amount of sampling, no, in order to get a good, relative good measure of our flow velocity. And this can be improved increasing the density of traces, or on the other way, increasing the number of frames analyzed. So we can play on both parameters, but the important is to set the optimal condition, the minimum number of or the density of traces to use, in order to get the optimal configuration for our applications. Another element that turned out to be relevant in this kind of application is the solar radiation and the zenithal position of the sun. And in particular, this affects the response of the particles and the signal of these particles. And according to this, there are particles that material that are more recognizable and works better than others in different configuration. And I will explain this later with an example. These are the two study cases that we have used. In particular, they differ for the specific characteristic of the water. One is turbid flow, and one is a clear water condition. And in both we used a black body, essentially, the charcoal, and wood chips that have a good reflectance, especially in at noon, essentially. And in fact, what we observed is that in clear water condition, the wood chips are well recognized because of their response at moon with the zenithal condition of the sun. Can be clearly recognized and provide the best performances in the reconstruction of the flow pattern at the surface. These are compared with a flow meter that has been used for comparison, with some problems at the boundary, as that's our experience, but I think it's confirmed by other application. And instead, in turbid condition, in turbid water condition, actually the charcoal traces were performing much better respect to the wood chips, and this is because of the contrast respect to the background of the image and the application of particle detection software that actually perform better in this kind of configuration. this is the final results, and I think that this kind of procedure has been extremely useful, because in this way, building a numerical experiment, we have been able to somewhat to isolate the small problems, or to identify a number of complexity in our analysis that allowed us to address the issue of optimal configuration and the specific configuration of a river system. Okay, I think that's all, and we can close the list of talks. Okay,
Thank you very much. Are there some questions to Salvatore?
Please. Oh, okay.
Thank you for the presentation. Just a quick question: have you considered like reflecting targets with and working during the night? Because that's what you would typically do with aerodynamics. Like in wind tunnel, you would have like reflecting targets, and you would illuminate those with lasers and stuff like that.
We didn't work during the night. That's something that I've seen in some publications that have been approached using thermal camera. I have to say that I think that the wood chips have a good reflectance during daytime, and in fact their behavior and their capability to perform better is due to the fact that they reflect and saturate the white more rapidly, and on the other side the charcoal is undistinguishable in clear water condition. That's I don't know if I answer your question, but we didn't use any reflective material that couldn't, that probably could not be environmentally friendly, because we had to disperse in the environment by natural material for sure. No, I get your point. I think for this reason, one option may be to use ice cubes, no, with thermal cameras. Is an option. It may be a bit more complicated, but it's for an experiment. It's an option. Okay.
Few other questions?
Okay.
Yes, Giuseppe?
Did you find any problem with the glint with the reflection of the sun on the surface of the water? Depending of the configuration, okay, of the zenith angle of the sun, I suspect. On the sea, this is it's happened very often, and then you can.
No. It may be an issue. It is true that we tried to fly at noon in order to avoid this kind of reflection issue. Honestly, most of the numerical simulation, of course, cancel all these problems that you may have in the field, and the aim was try to first identify the optimal configuration and try to use those configuration in our monitoring application, and that's what we did. As additionally results, we actually could compare the performances of different materials in the configuration. The noise induced by different factors in different environmental conditions has not been investigated.
Thank you. Salvatore, perhaps you can explain a little bit about the sampling kind of temporal resolution in terms of frames? How
Okay, that's
theoretically there's some kind of relationship in terms of sampling theory.
Absolutely. In fact, the fact that we observed this strong dependence between density and also frame rate and number of frames to reduce the total error of the techniques is due to the fact that the method essentially identifies the moving particles in each frame, and from one frame to the other estimates the vector, velocity vectors associated to the movement of each particle. By doing this, you can define a two-dimensional field of flow velocity vectors in a matrix. Of course, the number of vectors that you obtain is a function of the seedings, so the tracers that you have in your image. And the aim is try to have a proper number of seedings able to sample the flow velocity over your domain somewhat. And you can reach this result by either increase the number of frames obtaining as a result that the same tracer is giving you information over the entire matrix, or at least over the entire path that is following, or on the other side by using a larger number of seedings that can give you a larger sample of flow velocity vectors. The clear advantage is that you map the entire field of velocity and that you actually see a two-dimensional field of velocity, not just a module of the velocity in a few points.
But from a sampling theory point of view, if your velocity is psi x, if my frame works 2 times x, I should be able to capture everything, or is it something completely different?
No, by increasing the number of frames, you mean?
Yeah.
Of course, but this depends on always on the density of particles.
But
and
it should not influence the velocity itself, or does it?
What do you mean?
I mean, you have a flow with the velocity, regardless of your particles there, like that is, and you have more or less particles, just the kind of, you try to extract more or less information. It does not influence the velocity, does it? Unless in your numerical model, of course.
No. I see your point. The sampling time is always we are talking of less than a minute, because the frame rate we are working with is a frame rate of 60 frames per second.
Okay.
Or 30 frames per second. So it means that basically all the information we getting are based on less than a second sampling, because on the average mostly of the analyses are made with 20 frames in order to get the measurements. So we are interested in obtaining a nearly instantaneous kind of measurements. I don't know if I get your point.
I guess that's what's
okay.
presented. Yeah.
All right.
Yeah. Okay. Other
Okay.
questions? No. Thank you very much.
Okay. Thank you.
So by the schedule, we still have 7 minutes till 5:30. I don't know if there are some urgent questions to this session where questions were not asked about the speakers, or some other suggestions related to soil moisture flow and thermal imaging. Yeah, you had a question at a certain point also.
It's not a question, it's just a comment. I would like to comment that we should not forget that we can get soil moisture content also from the optical region and not also from thermal region.
Yes.
Okay.
Yeah, I guess as as a reaction to that is from both the optical part, thermal part, and microwave part, we can get soil moisture information. But also, as Antonino has mentioned, each of these parts gives you some kind of partial information. How do you tie all those different parts together? That's a challenge. I guess from a modeling point of view, you should be able to get the gradient there, both of the temperature and the soil moisture. If that is the case, then the challenge to the modeling community is that only hydrological modeling in terms of hydraulic water movement will not be sufficient. You should have a complete equation to solve the heat movement also. And of course, if you also want to use optical part to do that, it's just really the surface information that is important in terms of, say, bare soil. If it's vegetation, perhaps it's a different type of information. But from a physics point of view, they should be coupled together. So perhaps, Antonino, you have some ideas how we should put those things together?
Images. The reason we use both optical and thermal actually in the method is that when you use just the optical images, okay, the reflectance behavior changes when you are close to the saturation of the soil. When you are close to the saturation, the reflectance of the soil is going to increase strongly. So usually you have a decreasing in the reflectance with increasing soil water content. Then you get close to the saturation water content, and then you have an increase in the optical reflectance. So the relationship, these kind of relationships are going to work with the limited range of soil water content. That's my experience only. Yeah.
Some new applications on the optical vision. How you can compensate for the saturation?
With the short wave. Yeah, with the short wave. But I think that they are mentioning the 1,400 and 1,900 nanometers to compensate for this. Okay, and this is something that works in the lab, but you cannot use for remote sensing because you don't have downwelling solar radiation in that region. So if
it's disturbed by the water content of the atmosphere, that region.
Can you repeat?
I mean, these two wavelengths are disturbed by the water content of the atmosphere, if I understood well.
I'm speaking about the spectrum of the entire spectrum of the soil, and this is used recently by a couple of colleagues to show that you can actually extract the water content exactly from the optical region. I'm speaking about spectroscopy, not about bands, but this is
I mean, it's true. It's possible to derive the water content using the spectral signature, but following our experience, usually you need wavelength of bands that are located near the maximum influencing of the atmosphere. So if you collect images, hyperspectral images on that band, that algorithm cannot be used. You can use it for lab or for say special device in the field. Yeah. At 1.5, 1.9 micrometers, there is this problem.
Yeah, but if I can add a comment, another issue is what is the depth that we are able to monitor. I mean, it would be interesting to have a clear idea of what we are measuring. If we are measuring just the skin surface, it's an information that it may be useful up to a certain level. If we are measuring a depth that is representative of the routing depth, that's the information that is actually useful for precision agriculture activity and actions. So I don't know if optical can reach this level of information. No. That's an open question. It's.
We still don't use this facility on drones and also on airborne, man airborne. Only in the field. We can reach to the 5-10 centimeters with the millimetric waves. But the facilities we have today, I mean, it's a question. We cannot go beyond 1 centimeter, 2 centimeters. Maybe in sand soil we can reach a depth of a couple of more centimeters, but not in real soil with clays.
Yeah, I think it's kind of very interesting for this community trying to look at all the information from optical till microwave, because the information content gives a kind of a different aspect of the same system, so to speak. In terms of soil moisture in the routing zone, my understanding would be you either use a data simulation, a simulated kind of surface information into the routing zone, or you go to evapotranspiration, transpiration specifically, which is then tied to the soil water availability in the routing zone. So basically these two approaches could help you actually to really utilize the information. And then the challenge is that what kind of model do you need to be able to actually utilize this type of information? That could be quite interesting also to push the science aspect, not just the techniques and things, and what is really needed to improve the modeling in order to be able to utilize that kind of information. That could be something we can actually, I guess, do. We do some work related to more to really say the microwave part, but here there are a lot of colleagues doing thermal part, optical part, and then another part, I guess, that is not very much discussed is related to soil properties. My feeling is that if you use optical, thermal, microwave part, you should be able to identify soil physical properties quite well, and then take that through the pedal transfer functions to hydraulic and thermal properties. That would really improve your modeling. And in that case, your model parameters will not be arbitrary. There somehow the spatial distribution will be reflected into your model parameters. That could be something of fundamental importance. And currently, I mean, even in the land surface community, in the modeling community, they use a table. With that table, you use a certain type of land cover and a certain type of soil, and then those things are tied to some say parameters, hydraulic parameters, porosity, field capacity, wilting point, and all those things. That is quite limited, and here there's a real chance to improve the spatial temporal accuracy of that. And perhaps then we will be looking at the type of model you force it based on surface observation from a complete spectra to generate things that you cannot observe. And then the things you can observe, like profile information of soil moisture, soil temperature, discharges, will be actual validation information. So we change the kind of paradigm of doing modeling. And so far we try to mimic what we observe on the gauging station. Perhaps we can look at a different thing. I mean, we have 4 or 5 years of time to really work out something that could be quite interesting.
one strategy, one possible strategy that we learned, is certainly critical in order to predict and to get some information about the below ground, and so the something below the skin surface, is to look at multi-temporal observation. As we have seen from some of the results of Maltese this afternoon, actually the inertia of the soil gives us good information about what it might be the actual state of the soil. There is also some work that we have done on this specific topic using analytical models in order to use the fluctuations observed in the skin surface to predict what it might happen in the root zone. So this is also a possibility and a strategy that we can use, and it is used in other contexts.
Yes.
Just a comment about the extrapolation to the root zone. We should also keep in mind that most people think that soil profile is uniform, but this is not. So soil profile is layered. So this is why I caution to extrapolate data, soil moisture data from the uppermost soil horizon to the entire root zone. I made a paper in WRR 2 years ago, just demonstrate that if you do so, you can do that, of course, but with the larger uncertainties. And only some scaling can help just to reduce this uncertainty. So soil layering is reality, and soil profile uniform is just something that is only in our mind.
Felix?
Well, of course, the surface soil moisture is not exactly the same that the root soil moisture, but for different reasons. One of them you explained before. But actually, the surface soil moisture is influencing the bare soil evaporation, first thing. And the second thing, we don't need to, from the model point of view, we don't need exactly to use observation, the same observation that our state variables, because we can just it's possible to transfer information just from the dynamics in time and from the spatial variability of proxy information related with our state variables. That's the way. That's what we are trying to do, and you saw the first results in the Carlos presentation. Use proxy information for the temporal and spatial variability for our state variables.
But of course, I don't want to say that uppermost soil moisture is not important. Again, it depends on the target of your analysis. If you are interested in evapotranspiration as a whole, with, especially in our climate with the high temperature, evapotranspiration is a big percentage comparing to transpiration. So maybe the soil moisture in the uppermost soil horizon can help to understand some processes. Of course, if you are interested in transpiration, in plant transpiration, of course you need the amount of soil moisture in the entire root zone. So again, maybe the information only on the uppermost soil horizon can be so limited.
Okay, thank you very much. Salvatore, you have a final comment before we
no, I think
over to the organizers?
I think there is a lot of ideas, and there are also, what I see is a lot of potential interactions, because of course now we are closing with some curiosities and limitations of our methods in monitoring soil moisture, but we have the solution for almost a huge number of issues, and for the monitoring of several variables that compose the river systems. For instance, in terms of when we think about the root zone soil moisture, it is true that we cannot tackle the full problem from above, no? But we see a lot of information, like the vegetation is responding according to the soil state, so we can interact with each other. The different community can try to cooperate in order to try to identify the best practices in agriculture monitoring, because there are a lot of complementary information that can benefit from each other, no? And probably with this tries to stimulate this kind of interaction, we can overcome some of the actual limitation in science and Earth observation. So this is my take-home message. And I think that according to this, we can probably elaborate some good idea in the coming days, tomorrow essentially. So I will try to discuss with most of you tomorrow. We will probably circulate and have exchanges. We will not have closed working groups. I encourage to eventually to move during the discussion and checking out what is going on in the different working groups. But the good part will be that we will try to summarize at the end of the day of Friday. At noon we will try to collect all the ideas and try to identify a clear path for the next year. Probably Felix can give us some technical details about tomorrow, and after that I think it was a very productive day. I have to thank a lot of people. I have to thank the chair of each session, Bob, Antonino, and Pauline, that have been very very stimulating for the discussion. And so please, Felix, tell us what we have to do tomorrow.
Yes. Tomorrow we will split in 5 working groups, and the meeting rooms are in the Red Cube, which is just close to here, in the 4th floor. To don't be lost, first came to the 3rd floor, which is the only way to transfer horizontally, and then move to the red one. And unfortunately, tomorrow the big conference room are already booked, the 3 of them in this area. We need to move not to this conference room at noon. We'll move to a large meeting room for 40 people, and we are a little bit overcrowded there, which is again in the 4th floor, but in the green cube, in the north stream of this facility. Tomorrow at 9, from 9 to 12, will be in the red cube. From 12 to 1 will be in the green cube. Okay.
So
That's
at
all.
least there is some walking and a good exercise. Okay, thank you so much.
Okay, thanks a lot. Thanks a lot.
Thank you.
Okay, that's a nice day. Thank you very much. Okay, you're welcome. Yeah, I think we should utilize the momentum, and also tomorrow in the discussion, several of those questions discussed should be really looked into, and then try to seek some other opportunities and see, really do something together.
So, okay, good.